Okay, so problem one gave us some practice with Gauss's law. Problem two gave us some practice with Ampere's law. And now let's take a look at number three. So this is a Gauss's law problem. And what we have here is we have a parallel plate capacitor, like we saw earlier this semester. And on the inside of this plate is a positive Q charge, and on the inside of this plate is a negative Q charge. There's also a smaller positive charge on the outside of this plate and a smaller negative charge on the outside of this one. I did not draw those though, because as you can see, they're not going to affect our Gaussian surfaces. So we're going to do Gauss's law for these three different surfaces. So A will be the first one. And here we've got a box where one face of the box is, if you want to think of it this way, it's buried inside of this parallel plate capacitor. Or this plate anyway. And this plate is a conductor, okay? So there's a reason for putting it inside. And this is different than an example that I first showed you with Gauss's law, where I had the Gaussian surface go all the way through the plate. And so I had one face on the left of the plate and one face on the right of the plate. So this is slightly different. Here, one face is to the right of the plate and one face is inside the plate. And we'll see why that is a clever idea that makes the math a little easier here in a minute. So let's do surface A first. And the goal in part A is I want to know what's the electric field between the plates. And so that's why this surface is here, is because this is where I want to know the electric field. I want to know what the electric field looks like somewhere inside, in between the two plates. Okay, so here I've redrawn the situation in A in more of a 3D perspective way. So here is both of these sheets makes up the conductor, the capacitor plate. This is the inner plate, inner edge of the plate, and this is the outer edge of the plate. Dashed lines mean that we're seeing through this first edge a little bit. Here we have our Gaussian surface is coming out of the plate, and one face of that surface is dashed here to indicate that it's buried inside the plate, in between the inner and outer edges of the plate. Now the question tells us that we can make one assumption, which is that as long as we're not close to the edge, the electric field must be horizontal everywhere between the plates. So I'm just going to draw a couple here. And now we're pretty much ready to find the flux through this Gaussian surface. Okay, so to get the flux through this box, we need to consider all six faces, the flux through each of the six faces, and add them together. So I've labeled the faces right, left, front, back, top, and bottom. All right, so what's the electric flux? Let's do the left face first. The electric flux through the left face, well, this is why the left face, we buried it inside the plate, because the plate is a conductor and this whole system's in equilibrium. Therefore, inside the conductor, the electric field is zero everywhere. So the electric field on this face of the box is zero. So the flux must be zero. Okay, how about, let's do the front face. So the front face, I have an electric field that's going to the right. But what is the direction of n hat? Well, n hat is coming out of the page, okay, because it's the normal to this front face. And you see that E and n hat are perpendicular. So E dot n is going to be zero. Another way of thinking about this is that the electric field, since it's parallel to the face of this face of the box, it just skims along the face of the box. It doesn't actually go through the face. It doesn't go from one side to the other. It just skims along the face. So the electric flux on the front face is zero. And this one is because B is perpendicular to n hat. Sorry, E is perpendicular to n hat. And this one is because E is zero inside the conductor. And then how about the back face? So it did the front face. The back face is the same argument as the front face. Now the normal is pointing into the page or away from us, and the electric field is still to the right, and so those two things are perpendicular. So this is 0 because E is perpendicular to n hat. How about the flux through the top face? So E is to the right. For the top face, the normal is up. So right for E and up for n hat. Again, those are perpendicular, no flux. And we can see that E is just skimming along this surface, along that face of the surface. And then for the bottom, same argument, 0, because the electric field is just skimming along the face. So the only part of this box, the only face of this box that has any flux is going to be the right face. And that's the reason why this box was chosen. This shape, and also putting one face inside the conductor, is to really simplify the calculation for the flux. I went through all of these steps to show you why this is a simplification, but normally when you do a calculation like this, when you're used to it and you've been doing it a lot, you automatically know all these are 0, and you set up your surface like that so that they will be 0, and you just skip this step and you go right to finding this flux right here. Okay, so let's do that now. So what's the flux through the right edge, the right face? Well, E is pointing to the right, so it's basically coming out of the box, out of the face, and n hat is pointing to the right, out of the face. Okay, so those are parallel. So the cosine between them is 0. So E dot n is just going to be magnitude of E times magnitude of n, which is 1, times cosine of 0, which is 1. Okay, so it's going to be magnitude of E times, and now we got to integrate over the area, but E is constant over the area, so it just ends up becoming the surface area. Okay, so now we need to decide what the surface area of this box is. And it shouldn't matter for the same arguments I made before. This is a mathematical imaginary surface. Its area should not affect physical behaviors in the real world. So I'm just going to call this area A box. Okay, it's the area of the one face of the box. And if everything goes well and as it's supposed to, this area of the box should drop out in the final answer. Okay, so that was a rather long-winded way of getting to this simple result, that the total flux through the surface, through this Gaussian surface, is E A box. Okay, so that's the left-hand side of Gauss's law. The right-hand side is we need to figure out how much charge is enclosed in the box. Now, the charge lives on this inner surface here. And since the box does include the inner surface, then some charge is contained in the box. It might make a little more sense from this 2D side view. You can see that at least this part of the surface right here, these charges are inside of our box. Okay, so we need to figure out how much charge that is. Well, we have a total charge of Q on the inside edge of this plate, distributed over an area A, distributed evenly over an area A. So it's Q over A is the charge per area. So if I take the charge per area times the area of my face that is buried inside here, that should give me the amount of charge that is here. Okay. So the charge enclosed is the charge per area of the whole plate, or this inner surface of the plate, times the area of the plate that is inside of my box. So how much of the plate's area is inside of my box? Well, since this is a box and these lines are all parallel, then it's got to be A box is the total amount of the plate that is the total area of the plate that is inside of my Gaussian surface. All right, so now putting this all together into Gauss's law, I have the left-hand side, which is E times A box, is equal to the right-hand side, which is Q over A box, and then I need to divide by epsilon naught. And as expected, A box cancels. So our result is that the electric field in the space between the parallel plates is Q over A epsilon naught, which in the past, this is a positive Q. In the past, remember, we called Q over A, the charge per area, we called that sigma over epsilon naught. So this is the exact formula that we have seen before for the electric field between parallel plates. All right, now let's take a look at surface B, which is in the space between the parallel plates. You can see that B does not contain any charge. Okay, so that's going to be an important observation. And what they would like us to do is they'd like to show that the electric field everywhere in between the two plates is the same, which is a result that we've seen before. We came to it in a very different way using Coulomb's law, but we're going to verify this result here using Gauss's law. So electric field, remember, is pointing to the right everywhere between the two plates. And so over here on the left side, let's say I've got an electric field coming into the box, E1. And over here on the right side, I've got an electric field coming out of the box, E2. My goal is to show that E1 equals E2, because that would argue that for any box that I draw, if E1 on the left side is equal to E2 on the right side, then E must be the same everywhere between the two plates, because it's true for any box that I draw. Okay, so that's what we're going to show with Gauss's law. Okay, so what's the flux through this box? It's going to be the sum of the fluxes through all the faces, just like we did in part A. So notice that I didn't label these at the top and bottom and sides as E1 or E2 or E3 or anything. And the reason for that is because we know that the electric field skims across all of these faces parallel to them. So there's going to be no contribution on the front, back, top, and bottom face. Okay, so all of those fluxes are zero because E skims along those faces. And so all we have then is the flux coming in and the flux going out. Okay, so the flux coming, let's do the one going out first because it's positive. The convention here, well, we can see it by drawing in hat. On the right face, in hat points out of the box, which is parallel to E2. So the angle between these is zero. So the flux is going to be E2 times this area, which I called A box again. Whereas over here, we have in hat pointing to the left because it has to point out of the face, out of the box. Where E1 is going into the box, angle between these is 180. So cosine of 180 is going to introduce a negative sign. I'll go ahead and put my magnitudes on here as a reminder. And so I did this kind of the long way by using E dot n. But you can also remember the convention that if E is pointing out, then that's a positive flux. That's our convention. And if E is pointing into our surface, that's a negative flux. That's why I've got a positive flux here, a negative flux here. And I can factor out this A box. And I have E2 minus E1 on the inside, in my parentheses. And now how about the right-hand side? What is the charge enclosed by this box? Well, it's zero. There are no charges inside this box. So that means the right-hand side of Gauss's law is 0 divided by epsilon naught. So now I can divide both sides by A box. It goes away, and I'm left with E2 minus E1 equals 0, or in other words, E1 equals E2. So I've just proven a very simple way that the electric field in between the two plates is everywhere equal. Again, any features of the box have dropped out by the time I get to here, so I could have drawn any box that I wanted, and I would see that the electric field on the left edge of the box must equal the electric field on the right edge of the box as long as the box did not contain any charges. And that's right from Gauss's law. Okay, part C. We've got this surface now. So let's see what's going on over here. It's going to be very much like A. okay? But there's going to be two key differences. One is that this box now contains negative charges instead of positive charges. And the other is that up here I had E kind of going to the right, which was out of this box. Down here I have E going to the right, but that's in to this box, okay? And E is still 0 over here, just like it was 0 over here, okay? So there's two important changes. Otherwise, the calculation is going to be very familiar. Okay, so I've redrawn the situation. So I'm going to go through this one a little bit more quickly. First of all, what's the flux through this surface? This end, electric field is 0. And across the top, bottom, front, and back, the electric field skims along the face of the surface. So the flux there is 0. So the only place I'm going to get flux is on this left face where the normal is pointing out of the box. Okay, so here, as I alluded to earlier, E and N hat are in opposite directions. They're anti-parallel. So theta is 180. Okay, so the flux through the left surface then is magnitude of E times magnitude of N hat, which is 1, times the cosine of 180, which is a negative 1. Right? Times the area. The area is, again, I'm just going to call it A box. Okay, what's the charge enclosed by the box? That would be these negative charges on the plate here. And so I'm enclosing a piece of the plate with an area of A box. So since I know that the charge is evenly distributed across the plate and it has a total charge of minus Q over an area of A, there's my charge per area, times the area that I have enclosed, the piece of the plate that's been enclosed. And now I'm ready to put all this into Gauss's law. I have negative E, A box for the left-hand side. The right-hand side is minus Q over A box over epsilon naught. So this looks a lot like what we did before. Notice that A box cancels again. And these minus signs cancel. So it's important that we're careful about the minus signs here and the minus sign that comes from the flux here, because those minus signs cancel. And now when I write down E, I get Q over A epsilon naught, or sigma over epsilon naught. And this is what we would expect for the magnitude of the electric field inside. It should not be different than the answer we got for part A, right? Because as we showed in part B, the electric field should be the same everywhere between these plates. So we got one answer for A, which was this. Then we should get the same answer for C. Even though we enclosed the negative plate this time, this face of the box is still in between the plates, and just like this face is. So these two faces should have the same electric field going through them, and that is, in fact, what we see. All right, moving on to number 4. This problem is going to look very familiar if you watched my Ampere's Law video, because this is the magnetic field due to a solenoid. So I did that in my Ampere's Law video in one way. We're going to do it in a very similar but slightly different way here. In my previous video, I used the assumption that B is small outside of the solenoid. Remember, up here is outside and down here is inside. I have all these currents coming at me here. And I made the argument that B was small or close to 0 outside. Here we're not going to make that assumption. And that's going to add an extra step or two, but we will get to the same result. So part A is asking us about these vertical parts of our Amperian loop. What's the direction of B? So remember that B is, using right-hand rule number 3, B is to the right, inside, and it's to the left, outside. So that means along here, it's to the right, and along here, it's to the left. But we're traversing this loop in the counterclockwise direction. So right here, we're going up when the magnetic field is to the right. Here, we're going up when the magnetic field is to the left. So, and then we can make all the same arguments over here. So DL is perpendicular to B on the, I'll call these the vertical edges of our Amperian loop. Okay, now I'm going to calculate the integral of B dot dl going around this loop. So integral B dot dl going all the way around my closed loop. And we already have argued that since these are perpendicular on the sides, we're going to get zero contribution from those. So all that we have left is the contribution along this edge of the loop and along this edge of the loop. And remember, I'm not assuming that B is zero in this case. Okay, so I've got B inside times dl along this bottom edge plus B up here times the integral of dl along this top edge. And each of these edges is a length w. So this integral evaluates to w. This integral evaluates to w. And so I have 2bw. And here there's an underlying assumption that I've made that if this edge is the same distance from the currents as this edge, I'm assuming that because of symmetry, then B must be the same here as it is here, which is a valid assumption until I introduce the other half of the solenoid, which is what I'm going to do next. But first I need to finish using Ampere's law here. So I've got the left-hand side. The right-hand side is the total number of, the total amount of current that pierces the soap bubble stretched across this area. And we're going to calculate this exactly the way we did before. If we know that there's N coils total along this length, then we know that the coils per length is N over L. So the number that would fit inside a length W has to be N over L times W. So the net current going through our loop here, piercing the soap bubble, is going to be I, which is the current through a single one of these, times the number of them that fit inside, which is N over L times W. All right, so let's equate our left-hand side to BW and our right-hand side, which is mu naught N over L W. The W's cancel, which is to be expected, right? Because W was part of my, it was the dimension of my imaginary Amperian loop. And now I can solve for B. And I get mu naught over 2 NL. So I get half the result that I got in my previous video when I assumed that the magnetic field was 0 outside. Now we're going to do the other half of the solenoid. Okay, so here's the entire solenoid now. I've got these currents coming at me and these currents going away from me. They come out of the page, they go down around the cylinder, go back into the page, go up on the far side of the cylinder, come back out, go down the near side, into the page, and so on. And we found that the magnetic field here, due to the top charges, so I'll call that BT, B top, was mu naught over 2 N over L. What about the bottom? So the bottom, I can repeat this calculation, okay? And I'll get the same magnitude inside and outside as I got up here, okay? This is the magnitude. Yes, these are negative currents instead of positive currents, but I'm just worried about the magnitude, okay? What's the direction of the magnetic field due to the bottom row of currents? Well, if I use right-hand rule number 2, first let's use it on the top row just to see where this right pointing direction comes from. If I point my thumb out of the page, my fingers are curling counterclockwise. And so you can see inside the coil, my fingers are pointing to the right. Down here, if I point my thumb into the page with the current and coil my fingers clockwise, they are going clockwise this time, you can see that they're pointing to the right in between. Okay, so that means B bottom is equal to the same thing. So the two are going to add. So the B inside is equal to 2 of these, which ends up, oops, I forgot my I, which ends up becoming mu naught n I over L. And I forgot my I on the previous page too. There we go. Okay, so we've discovered this result that I did in my Ampere's law video, this time without assuming that the magnetic field was 0 outside. Speaking of which, what is the magnetic field outside? That's part D. So outside, down here, I've got my magnetic field due to the bottom row is going to be to the left, right? Again, right-hand rule, point my thumb into the page, fingers are curling to the right when they're inside, but when they get down here, they're curling to the left. How about down here due to the top? Well, here I've got my thumb points out, my fingers are curling, so down here, due to the top, my magnetic field is to the right. Okay, and if they're, again, each mu naught over 2 ni over L, but they're opposite to each other, then you can see that the net magnetic field outside is 0. And we can go through the same process up here on this side of the solenoid. So the magnetic field due to these top currents here is to the right, using the right-hand rule. And due to the bottom currents down here, it's to the left. Okay, so they flipped, but they're still opposite and equal. So the net is 0. So B equals 0 outside. And so the assumption that I used to simplify the math in the previous video is a valid assumption. And we arrived at the same result both ways. One last remark is that this is in the ideal case. In the actual case, it's going to be approximately equal to 0, because remember, when we have a solenoid, the magnetic field, it comes out of one end, goes in the other end. But we know from Gauss's law of magnetism that all of these magnetic field lines must be complete loops. So they must loop around and re-enter. Okay, but what we've found here is that this loop back portion is going to be very small. The real magnetic field strength is going to be inside and just off the edges of the solenoid.